I haven't looked at these yet, so I may, I don't know. I just
It's
haven't
like
had time.
impulse and momentum.
Yeah.
So, have you talked about impulse already? Like momentum and impulse?
A little bit, not much. We're just reviewing right now.
Oh, okay. So, actually momentum and impulse are like way easier than forces.
Okay.
So, you'll do impulse and momentum, and then you'll do kinetic, or like energy. And energy is the best. It's like the easiest thing that you do in the class. But basically, the momentum of an object is its mass times its velocity. So it's like P is what we use for momentum. And the way you find it is you just take an object's mass multiplied by its velocity. And so if you have something that weighs like 6 kilograms going this way at 3 meters per second, then it'll have a momentum of 18 kilogram meters per second in that same direction. It's like super easy.
You could add it. Oh,
Well, yeah, you multiply them.
Multiply them.
None of these. We got 5 colors of marker here. One of them works. And then impulse, they call J. And impulse is basically like when you have something like a baseball hitting a bat. I guess the bat hitting the baseball. It's only in contact with the ball for like, 6 milliseconds or something like that. But what happens is if you have the force versus the time, it hits the ball and it increases its force. And then eventually, as the ball kind of springs off, the force decreases until it loses contact again.
Okay.
So this would be the force versus time graph. So impulse is all the area underneath this. So that's your impulse. And so if you have the force times time, that gives you units of kilogram times meters per second. Look like this. You're right either way, but which is the same units as for momentum. So impulse is actually the change in momentum. So if you have like a baseball going this direction, 20 meters per second, let's crank that up a little bit. It's only like 40 miles an hour. Let's call it 40 meters per second. And it's coming and it's got a mass of like 0.2 kilograms. And then it hits a bat, and the bat hits it with like this impulse. Let's say this area was like, let me see here. Let's say this area was like 2.4, something like that. So what you do is you take this momentum. So P here is 40 times 0.2. Oh. I think it's 24. So 40 times 0.2 is 8. No. Yeah. Yeah. So it's 8 going this direction. Then there's an impulse that hits it this way. So the change here was it goes from 8 going this way, it adds 24 going this way, so you end up with a momentum of 16 going that way. So we'll talk about it more. We can set like problems and stuff, but it might take just a couple minutes to get used to it and kind of see what the ideas are and stuff, but it's super simple.
Okay, cool. Assuming that this force is constant, what is the magnitude J of the impulse on the ball? Maybe you have to read all this.
No, I think just the top part. So that the left side stuff is explaining impulse.
Oh, okay. Oh, okay. Parts A, B, C, consider the following situation in a baseball game. A batter swings and gets a good solid hit. His swing applies a force of 12,000 newtons to the ball for a time of 0.7 times 10 to the negative 3 seconds.
Okay.
Define J.
That says assuming that the force is constant, what is the magnitude J of the impulse on the ball? So, what did I just, so J is impulse.
Oh, so just use these equations right here. So F, do you just use that one?
Yeah. So this would be F.
So 12,000 times D?
So it's, I mean, it's that simple.
Okay.
But remember how I said like it's this area underneath the curve?
Right.
So what we're saying in this case is that your force is 12,000 the whole way. So here's your force, is 12,000 newtons, and your time is 0.7 times 10 to the negative third seconds. So if you wanted to find the area under this curve, you just multiply them together, right?
Right.
So that's how it works. So you can do that with any shape graph.
That's nice. It's 8.4. Does that sound right?
8.4. Yeah. Yep.
We often visualize the impulse by drawing the graph of force versus time. For a constant net force such as that used in the previous part, the graph will look like the one shown in the figure. Is that done by the textbook? Figure F1.
Oh yeah, it might be. No.
Right.
Usually their figures are like right there. And there isn't any more to scroll down on the left. Huh. Oh, basically it would be this picture. So yeah, 12,000 newtons.
For this graph, the blank of the rectangle corresponds to the impulse. So height,
The height, what is the height on this graph?
this graph. F is height.
Yeah, so your height is the force,
Oh, so would it be area?
right?
So, oh, okay, so that's talking about that impulse, like all of it.
Mm-hmm.
Okay. More realistic graph for the force that the swinging bat applies to the baseball will show the force building up to the maximum value as the bat comes in full contact with the ball. Then, as the ball loses contact with the bat, the graph will show the force decaying to zero. It will look like the graph in the figure.